So I want to finish showing how to do expanded decomposition fast. And again, the goal is that we want to solve this, right? We want that given a graph, a node weighting, parameter phi, then you can compute a cut such that, you can control the cut size, and now we want maybe A here is not quite phi expanding, but phi over log square expanding. But you want it to be fast, right? Yeah. And we see the algorithm that, like, the algorithm that we have seen before is just if there is a phi sparse, like if you check if it's expanding. If it's expanding, then we're done. If not, then there is a phi sparse cut, right? And if there is a phi sparse cut, then you cut it and recurse on both sides. Like cut through phi sparse cut, and then recurse on both sides. Recurse here and here. Okay. So as you cut along, like you cut along the phi sparse cut, and that's your cut and recurse here. We can say that the total number of edges that you return, the total cut edge, is going to be at most. So if this is C, like the cut here, and when you recurse here, the size of C is just going to be this much, right? Actually, can any of you recall how can you prove? How do we get this bound?
Just vacuuming. It's just vacuuming like cardinals and bits.
Yeah. We kind of somehow like get a charging argument, right? The idea is like because you cut along sparse cut, you can charge the edges that you cut to node weighting because it's sparse with respect to the node weighting, and and you like each node weighting is kind of charged by this factor phi because it's phi sparse, and each node weighting unit is charged log n times because you charge to the smaller side. Okay, and this we see that this is hard, but if you just want this, like if you relax the goal here a bit, that is, you just ask if A is phi over log square expanding, and or otherwise phi sparse cut, then here we can do it fast now. Using cut matching game. But even if we can find a single sparse cut fast, doesn't mean that you can get expanded decomposition fast, right? Because you might need just to find, like you find a cut, you recurse here, you find a little cut, recurse here. Just need to recurse. The recursion depth is like n, so that's bad. Okay. On the other hand, if we know that somehow, luckily, the sparse cut is always balanced, then here the recursion depth is good. Like if it's balanced like this, the recursion depth is log n. So now everything will be fast. Okay, and we got stuck. Like here is the question. What if there is no balanced sparse cut, right? What if we cannot get to this case? And if there is no balanced sparse cut, it turns out that it's a good case too. If it's balanced, it's good. If there is no balanced sparse cut, it's also good because there must exist a giant expanding set. And yeah, if there's no balanced sparse cut, there exists giant expanding set. This is like a two thing that must happen. Okay. And formally, we see this. That is, if for any graph, actually, you can always find some set S that is like a sparse cut. And there can be two cases. That is, S is either balanced or S is tiny, but then its complement is already expanding. Okay, so this is what we proved last time. Okay. Question about the statement. Okay. So good. So now I'm gonna skip this because we show the proof. And actually, okay. Suppose that, like, by the way, like if you change the parameter 1/5 to something smaller, it's also correct. Okay. Now, here is the point. Suppose let's say that I use S to denote this cut. S is like a cut from this subroutine that either returns balanced sparse cut or giant expanding set of this parameter. Okay. Just when you set beta to be 1/5. Okay. So suppose that you can compute it fast. I just show the existence here, but suppose that you can compute this thing fast. Okay. Then you can compute expanded decomposition fast now. Any intuition why this should be the case? So do everyone agree that if we always get the first case, we are good? Okay. Why it should be the case that if we get a second case here, it looks good too? Why? Sam?
Can you reverse on the smaller of the two halves of the cut?
Exactly. Yeah. Like, it can be the case that S is tiny and the complement is big, but we don't need to recurse on the big side anymore. It's already expanding. We are done there. So just recurse on the smaller side. Right. So the recursion depth is going to be still log n. That's the idea. Let's see picture. Like, if you get balanced cut, then it's good. You recurse on both sides. If it's balanced again, it's good. But it can be the case that it's not balanced. But if it's not balanced, this part is already expanding. So we just need to recurse on the smaller side, which means that, and just goes on. And it means that each, like the size of the node weighting for each component that we recurse will decrease by a constant factor, right? So the recursion depth is log n. And the total time per level, we said that we just need to do some cut matching game, which is we just call max flow polylog times. So the time here is linear, the time here is linear. So total is just linear in the graph size. So the total time per level is linear, almost linear. So the total time is just good. And the correctness is also kind of clear too, right? Because we're gonna still get that the size of C is small, because we only cut through sparse cut. the same charging argument holds. Right. Okay. So the same proof applies. And for each component, as at the component after we don't cut anything, I claim that the node weighting is going to be expanding in that component. And that's clear because that's the only reason we stop the recursion. We stop the recursion, we don't cut if it's expanding, right? So every component at the bottom here is expanding. So is it kind of intuitive to you now that now the goal is just to solve this subroutine? Balance cut or giant expanding set? If you can do this fast, you're done. Okay. So that's the question. Can we solve this thing fast? Can we find this thing fast? The question answer is yes. Yeah, we're gonna see it, but it's kind of not quite, almost actually. Okay. So in what sense? Okay. Everything so far is the same. I just gonna say that we do the same thing, we find the same thing. Everything here is the same. What's not quite the same is next. Is that first, the expansion guarantee naturally decreased a bit. It's getting worse a bit by log square. So that's expected because we use cut matching game. But more important thing is that here, this is expanding in G, not in, this is not in, we used to have this one, right? We want this in this component, A in this component to be expanding in this component, but we're gonna just guarantee this one. So not, this is weaker. This is weaker, right? Because it's you can send flow in the whole graph instead of sending flow restricted into this subgraph. Okay, so we get something weaker here. Okay, but we're gonna do this in time that is fast, cut matching game time. Now, this is the part where I want you to think, and I'm gonna put it in the homework actually, how to do it. Because you have seen how to use standard cut matching game to find one sparse cut, just single sparse cut. It might be balanced or not, doesn't matter. And you have seen a more advanced version actually to find expanding balance separator. The cut matching game that use both deletion and moving, transferring vector. It turns out that to prove this one, you just need the one that, you need to apply cut matching game with deletions only. And try to think about this. It will help you really understand the content of the class. Okay. So think about this, but so I will not prove this for you. You see how to prove it on your own. Okay. But now, what I'm going to tell you actually is here, how to change from this thing to what we want, to this thing. Okay. Instead of a graph G, it should be expanding inside the component instead, not in the whole graph. There's a way to fix this. And that's it's a technique that people I and Di Wang introduced. It's called expander trimming. Yeah. Okay. So here's the point. The point is that think this is the set, and think of this as a set U, right? And what we have is that we have U such that the node weighting in U is expanding, the node weighting in sec U is expanding in G, but we want that, we kind of want that this is expanding in G induced by U. Okay. That's a kind of generic situation. We want expansion inside the component. This is S, this is U. Yeah. So whenever we want expand, like whenever we want to get expansion inside, like this, that's when we use expander trimming. Now I'm gonna tell you what it is. Okay, so the statement is like this. Suppose that you have the set U. You think of U in our context, U is B minus S, right? Okay. You have a set U, but the node weighting A in sec U is just expanding in the whole graph. So the flow might go out of U. Yeah. Okay.
Is there a reason why we're saying that A intersect U is cut expanding then if we're talking about?
Oh, good. Actually, good. I really mean cut expanding. Yeah. But having flow expanding is stronger, but actually it works for cut expanding. Yeah. So for cut expanding, it means that if you take any cut, it's expanding, but you might count edges that go out of U. Okay. Not just edges inside U. Yeah. Okay. So it's cut expanding in G. Now what we do is that we can find a set P. Think of P as like something that you prune out, like something that you don't want. Okay. And U prime is like the complement. This is U prime. You prune P out of U, and then you're going to get expansion inside. That is, now A intersect U prime is now expanding in G induced by U prime. So we just get expansion inside. And moreover, the cut size here will not increase. The boundary of U, like this is the boundary of U. If you look at the boundary of U prime here, it doesn't grow. Also, the thing that you pruned is going to be quite small, not too big. How small? Well, something like, it depends on how big the boundary was. Okay. So think of this thing as the boundary of U, and how much you prune out. It should be not too big compared to the boundary. Yeah. So in our context, when we think of using this thing, when we think of like our set U here, right? It's just going to be the set where this is V minus S, and this is S. So this is going to be sparse cut, right? So in our context, this is sparse cut, and the edges along this cut, you should think of this like it's quite small. The boundary here is small. Okay. Okay. Anyway, and we can solve all this in one Maxflow call. Okay. So good. Is it clear, the statement? Is it too abstract? Is it clear? can you absorb it? We used to have A that is expanding in G. In particular, the expansion is not just inside GU. And the point is, we're just gonna fix this by pruning something out, pruning some small thing out. And then now, what we want is true for U prime. That's it. Okay. 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 Do you want to see how this is proved first, or do you want to see how to use it first? Someone. How to prove it first? Yeah. Okay. 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 Let's see how to prove it first. Okay. Question? Okay. So here's the algorithm. It's just this. So you imagine that you send, try to send flow, like compute max flow and min cut, where the source is on the boundary of U. Just imagine that each edge here try to send flow. Right? And the sink is inside U, but I scale it down by phi over 2. Okay. The sink is just a node weighting in U, scale it down by phi over 2. So I just literally just compute one max flow. And now, just compute one max flow in GU. Okay? And I might get min cut. But this min cut might be empty too. But it's just P is just some cut. Whatever that cut is, just prune it out from U, and that's it. Okay, so let's see one intuition. Suppose first that, okay, this is U. Yeah. Yeah. And so instead of saying that the source is this, you can think of I actually have a split node in each of these edge, right? And then each of these node try to send flow to the graph. Okay. Okay. So the source is on this, maybe this split node. And the sink is just phi over 2 I intersect U. Okay. Suppose that the min cut is empty. Suppose that you can send flow successfully. Okay. Suppose that, meaning that there exists flow that saturate the source and respect the sink. Okay. If the min cut is empty, then it means that you only have the flow after min cut, right? The flow after min cut will saturate everything, will just saturate all the source and respect the sink. Okay. And I will now show that if that's the case, then I say that A intersect U is expanding in GU. So if I can send flow successfully, I just prove that instead of having expansion in G, it's actually expansion in GU. Okay. So why is that the case? Let's prove by contradiction. This is cut expansion. Okay. It's quite important. This is cut expansion. I don't know the proof of flow expansion. Okay. So, suppose that it's not cut expanding. It means what? It means that there must exist sparse cut here, inside this. Can a sparse cut just look like this? Can it be disjoint from the battery here? No, because it was not, like it was expanding before.
Yeah.
The only edges that the only cut that was expanding but not, that was expanding in G but not expanding in GU must be that it must kind of contain these edges. Right? Because I used to count this thing and now I don't count this thing. Okay. But so suppose that the cut S such that is sparse in this graph. It means that like there are so few edges here. It's sparse in U. But we know that it was expanding in G, so it means that there must exist a lot of edges here. So this is a graph where like this is a set such that there is a lot of edges here, and there are so few edges here. Can this happen? Why this shouldn't happen intuitively?
Because we can't send this flow through that.
Exactly. The flow here can be sent successfully to this graph. But if there are if there is kind of bottleneck here, the flow shouldn't be able to send. You shouldn't be able to send flow here. But we need to be a bit careful. Because this is a sink, right? So actually, the flow from the battery might be absorbed inside this thing too a bit. Okay. But think of this thing as quite small because I scale it down by quite a lot, right? I scale the sink down here by quite a lot. So the flow can be absorbed inside this thing by a bit, but the rest need to go out. But there is a bottleneck here, so that cannot happen. The flow need to go somewhere. It can be absorbed here just a bit, but it cannot even go out. So that's impossible. So that's intuitive reason why there must be no sparse cut. Okay, so take that intuition. Now we prove it formally. Okay. So suppose that there exists some set S. Okay. Maybe. Okay. By the way, but here I assume that P is empty, but here P is not empty. But actually the same reasoning can be said because when you have P here, you know that all edges from the min cut, the battery here, the red battery, can send flow to its complement, to U prime. Right? This is just the same situation when I said that P is empty and all the source can be sent, there is a flow that saturates the source from here to here. And now I just think of this as a source. Right? The source from here can be sent to here.
So if P is not empty, the source is different, or
If P is not empty, instead of the source is the battery of U, I just think of the source is this battery.
okay.
And you can see that it's just the same situation now, where this source successfully sent all the flow
Into U.
to U prime.
U prime.
Okay. And what we just need to show is that there is no sparse cut in U prime. So it's really the same situation. Okay. Okay, so what do we have? So suppose I consider any set S, maybe any set S here. Okay. We know that the cut size of S is big compared to node weighting of S. So the cut size of S is big. When you count everything here, this is quite big. But the cut size has two parts, which is the green part here and the green part here and the blue part. Okay. This is just true because A intersect U is expanding in U. Okay. A intersect U is expanding in U. Okay. But at the same time, we know that the blue part here need to be smaller than this thing. Because why? Because the blue part is like the source. Okay? And the source need to be like, okay, this flow here can be sent to this part. Okay? And what's the sink? It's like the source. This is like a source. And there is some sink here. So, okay, but what I want to say is the source is either absorbed inside S to some sink inside S, which is this much, or it must go through edges in the green part. Okay, so every unit of flow that starts from the blue part is either absorbed here, inside, or going through this. Okay, so it cannot be the case this part is smaller than this. Are we good? Like this is the green part, and this is the So each unit from source either absorbed is absorbed in S. How much it can be absorbed in S? This much. Because this is like a sink capacity inside S. Or go through the cut, which is this cut, this green cut here. because we know that when we have like this is there exists a flow after min cut, that this flow every source here is successfully sent to sink. So the flow is either successfully sent inside the sink here or going through this green cut. Yeah.
Shouldn't it be exactly equal? Why is there?
It can be bigger. This thing could be bigger. Like for example, if there are like a bipartite complete graph here, it's okay. Yeah. Okay. But once you have this, then you are done. Because you just kind of combine this thing together. Like this part is at most this. So you just replace the blue thing by this one. So you get that phi AS is at most 2, the cut size, plus phi over 2 AS. And then it just means that the cut size here is at least phi over 4 AS. So it means that this cut is not sparse. It's phi over 4 expanding inside the induced subgraph of U prime. Right? Even if you count edges inside U prime, it's big compared to AS. Make sense? Okay. Okay. So should I go on? Are we good? Okay. So next, I'll let you think about this. But it follows quite easily, actually, that the cut here doesn't increase, and the size of A, the size of P here is small. Actually, you have this one. Okay. So why this should be the case? Well, yeah. Anyone see some intuition why this, which is stronger than both of this, should be true? Yeah,
So if you can route this flow to the rest of the graph, then I think that we couldn't route that flow from the earlier boundary to the graph. But this time, like, we can route the flow from the new boundary.
1 second. Which flow? Which flow are you talking about?
The source to...
Like the source from here?
Like when we compare...
Or the source here?
Yeah, like I'm just comparing both of them. Like,
Yeah.
Since we couldn't do that, and we can do this in the present case after the cut, so it should somehow imply that previously the flow we sent out is greater.
I'm not sure which flow you're talking about. So which source, which sink?
Yeah, so the flow that we sent out in U, like
From here.
U,
Yeah. Mhm.
that like couldn't be routed in U.
Yeah, because it got stuck here.
Yeah, it was stuck.
Yeah.
But the new one can be routed, so
Right.
it should mean that the new flow is like smaller than the previous one.
Mm-hmm.
The boundary of U prime should be smaller than the...
Right.
Okay.
That's good. Yeah, you have a correct intuition. It's like you said that when we try to route from this battery,
Yeah.
and we get stuck, we will get stuck only because like the capacity on this cut is smaller than the capacity here, right? The flow from this part got stuck here only because if this is A and this is B, the only reason that we get stuck here is because A is less than B. Oh, sorry, B is less than A. There is a bottleneck that prevents the flow from here to here. So it means that's why like this part B is smaller than A. But we know a bit more actually. We know that if this is A, okay, A is less than B is less than A, but this is true even when you add this much. Because we know that, like, consider the flow before min cut, right? The flow before min cut here will saturate the sink here and the cut here. So it means that this is like every capacity on the cut here and the sink capacity in P, which is this much, is saturated from this unit of flow, from A. That's why A must be bigger than both, than this plus this one. Okay. You see, like, do you see this? No, right? Yeah.
Because like we know that routing to everything in P and then also across B, we're saturating all of that for this to be for the Minkai. Or
I mean, so how should I say this? Like, you remember like when we have a min cut, we have the flow before min cut and after min cut, and the flow before min cut is such that the FL, the flow before min cut, this is flow before min cut. The flow before min cut will saturate the sink L, but respect the source L. What's the sink L? The sink L is just the sink here and also this thing, which is just this plus this. And it respects this one. If it saturates this one and respect this one, it means that the source is bigger than sink, which just means that A is bigger than this thing. Okay. Okay. But if A is bigger than, if this A is bigger than this B plus phi over 2 AP, then you get this one. Because this part is just the same for both. Like, yeah. Okay. Like this part contribute to both boundary of U and boundary of U prime. Okay. Okay. So we get how to do trimming. And once we have trimming, so we have two ingredients. One is trimming. One is this balance cut or or giant expanding set. How do you think we should combine them now?
like we do our balance cutter expand and then we get some set that's flow expanding in G. We trim that and then we recurse on the small segment plus whatever got trimmed out.
Exactly. Yeah. It's just combining in the it's just combined in exactly what Kate said. We compute this balance cut or giant expanding set S. If it's balanced, we just cut on S. That's balanced sparse cut. Just do the same thing. That's good. Okay. If we get giant expanding set, but it's not expanding it's not expanding inside. is expanding in the whole graph. So we trim. Okay. So we get this one. This is S. This is U, which is V minus S. This thing is expanding in the whole graph. So we trim it. Okay. We trim it and we get P. And this is then U prime. U prime, which is V minus S minus P. And this part is now expanding inside U prime. So we are done here in U prime. So what we need to return is just we cut through this thing and we recurse only in this part, in this small part. Now, instead of setting beta here to be 1/5, I changed data to be to be something like 1/log square. Why is that? This is because the size of P here, actually, the size of P here is something like 2/5 times the battery of U, right? So how should I say this? If beta is too big, it's bigger than this one. Sorry, this S here, I forget to say. S cut matching game here is just the factor log square from the cut matching game. Okay. So we need beta here to be not too big, because otherwise, we might prune everything. Okay. Just need to set beta to be small enough so that when you get a set S, we know that this set is not too big, and then P here is not. It's just P here is still not just everything. We don't prune everything. Okay. So I hope it makes sense. Question about intuition first before we go to analysis. Okay. So first of all, the cut size is just gonna be the same, because we just cut through sparse cut. In the balance case, we just cut. It's just a sparse cut. In the expanding case, this is a sparse cut, and we know that the battery, when we cut through P, when we prune P, the battery doesn't even increase, so it's even sparser, right? The size of the set is getting larger, but the battery, the cut size here, is the same, so it's even sparser cut. Okay. So we cut only through sparse cut, and the expansion is just clear, okay? Because we use trimming. Okay. And the time now, each component, when we recurse, the component will decrease its size by something like 1 minus 1/log square. This is a beta factor that we. So recursion depth is something like this much times log cube. Okay. And so the total time per level is just cut matching game. So now the total time throughout is just the level times the time per level, like the time per one level, which is this. Okay. Questions? Okay. I have a feeling that I'm going too fast. Is that, am I? Okay. Okay. Let's maybe finish for today then. So we get fast expanded decomposition. I'm just gonna talk about some open problem next time, but for now we basically, once we get fast expanded decomposition and fast expanding balance separator, it's almost like the whole theory that we have developed so far. You're just gonna get fast algorithm throughout, except one thing, a three-cut specifier, three-flow specifier. We don't have that yet. We will do that next week. And everything, the whole theory is fast. And after that, we're gonna do so far everything is fast because we assume max flow. After that, we're gonna try to develop fast max flow itself. Okay. All right. Okay. See you next week. Yeah.